You know, in electromagnetism, there's this really fundamental question. Where does energy actually live? Today, we're going to dive deep into the energy stored in a capacitor. We're going to start with a pretty intense life or death application, then derive the core physics from the ground up using some calculus, and finally use that knowledge to solve some actual problems. So here's the plan. We'll kick things off with a life-saving device to frame our main question. Then we'll get into the physics of where a capacitor's energy is really stored. After that, we'll build the key equations from scratch, put together a handy problem-solving toolkit, and then we'll put it all to the test. All right, let's be honest. Potential energy can sometimes feel a little abstract. So let's ground it in a real-world scenario where its rapid controlled release is literally the difference between life and death. So I'm sure you've seen one of these around, an automated external defibrillator, or an AED. The absolute heart of this device is a really powerful capacitor, and its whole job, its only job, is to store a very precise, very significant amount of electrical energy, and then just unleash it in a split second to reset a chaotic heart rhythm. It's the perfect physical example of what we're talking about today. So that brings us to the big question, right? 400 joules is a serious amount of energy. We're talking enough to lift a 40-kilogram person about a meter off the ground. How can a portable device like that pack such a punch and release it almost instantly? The answer isn't in chemistry, like you'd find in a battery. It's all about the physics of the electric field. Okay, so where is this energy actually being stored? It's not in the metal plates. It's not a chemical reaction. The energy in a capacitor lives in the electric field itself, in what looks like just empty space between its conductive plates. The energy is stored as electrostatic potential energy. Think of it like this. As we push charge onto the capacitor's plates, we have to do work against the repulsion of the charges already there. We're fighting to build up this electric field. Well, that work doesn't just vanish into thin air. It gets converted into potential energy that's stored in the field itself. If you disconnect the capacitor, that energy just sits there, waiting in the space between the plates, ready to be let go. So, how do we actually put a number on this? We use this concept called energy density, which we denote U sub E. It tells us exactly how much energy is packed into every single cubic meter of that field. For a vacuum, it's 1/2 times epsilon naught, that's the permittivity of free space, a fundamental constant, times the electric field strength squared. Now, this isn't just some random formula. It's a profound result that falls right out of Maxwell's equations, and it confirms that the electric field itself is a real reservoir of energy. Okay. That energy density formula is great, but it's got a catch. It really only works for a uniform field. To get an equation for stored energy that's truly universal, we need to build it from the ground up, with calculus. This way, we'll get a formula that works for any capacitor, no matter what its shape or size is. So let's imagine we're charging a capacitor by moving tiny little packets of charge, dq, from one plate to the other. That very first packet is easy, there's no potential difference yet. But as the charge builds up, a voltage V appears, and it starts taking real work to move the next little dq against that potential. The tiny, infinitesimal bit of work done is just dw equals V dq. So to get the total work done to charge this thing all the way up to a final charge Q, we've got to add up all those tiny, infinitesimal pieces of work. And what's the perfect mathematical tool for that? Yep, integration. We're going to integrate V dq from a starting charge of 0 all the way up to our final charge Q. All right, let's walk through this. It's actually pretty elegant. We start with our integral. We know from the definition of capacitance that the instantaneous voltage V is just the instantaneous charge Q divided by C. So let's substitute that into the integral. Now, since C is just a constant for any given capacitor, we can pop it right out front. Then we just have to integrate Q dq, which is simply Q squared over 2. Evaluating that from our starting point of 0 to our final charge Q gives us this beautiful result. The total work is Q squared over 2C. And this, right here, is a perfect application of the work-energy theorem. All that work we did to assemble the charge on those plates got converted directly into potential energy, U sub C, stored in the capacitor's electric field. And this gives us our first and most fundamental equation for the energy stored in any capacitor. All right, now that we've done the heavy lifting and derived our main formula, we can use some basic algebra to create a whole toolkit of energy equations. This gives us the flexibility to solve a problem no matter what information we're given. So, starting with the one we just derived, U equals Q squared over 2C, we can just play around with it using the most fundamental capacitor definition there is. Q equals CV. By substituting for Q or for C, we can generate two other incredibly useful forms of the same equation. This gives us three equivalent tools, each one perfect for a different situation. So why have three? Well, it's all about being strategic. As you can see here, the best formula to use really just depends on the variables you're given in a problem. Choosing the right tool from the start isn't just about saving time, it's about minimizing the number of steps you have to take, which seriously reduces the chance for a calculation error. And hey, as a quick sanity check, let's make sure everything we've done ties back together. If we take our general formula, say U equals 1/2 CV squared, and we plug in the specific expressions for the capacitance and voltage of a parallel plate capacitor, well, the algebra just beautifully simplifies. What you find is that the total energy is just the energy density we started with, 1/2 epsilon naught E squared, multiplied by the volume between the plates. It just works. It confirms our whole framework is consistent. Okay, enough theory. Let's get our hands dirty and actually solve a couple of problems with this new toolkit. In this first example, we've got 3 different capacitors, and they're all hooked up in parallel to a 12-volt source. Now, because they're in parallel, we know the voltage across each one is exactly the same, 12 volts. That makes the formula U equals 1/2 CV squared the perfect tool for the job. Applying it to each one, we get their stored energies, 72, 144, and 216 microjoules. And because energy is a scalar quantity, it just has a magnitude, no direction to worry about, the total energy stored in the whole network is just the simple sum of the individual energies. Add them up, and you get a total of 432 microjoules, a really straightforward application of our new toolkit. And now, for the main event. Let's go back to that defibrillator from the beginning and finally solve our initial problem. We know the device delivers 400 joules of energy, and we know the capacitor was initially charged up to a whopping 10,000 volts. So the question is, what's its capacitance? Okay, let's think this through. We know the stored energy, U, and the voltage, V. Our goal is to find the capacitance, C. So we look at our toolkit and which formula connects those 3 variables. Bingo! U equals 1/2 CV squared. A little bit of quick algebra to rearrange for C gives us C equals 2U over V squared. Now it's just a matter of plugging in the numbers. So we plug in the numbers. 2 times 400 joules divided by 10,000 volts squared, and out pops our answer, 8.00 microfarads. It's really a testament to that V squared in the formula, isn't it? It shows how a relatively small capacitance can store lethal, or in this case, a life-saving amount of energy, as long as you can charge it to a very, very high voltage. All right, so this brings us to a final thought experiment, something to chew on. We've established that the energy really lives in the electric field. So imagine you charge up a capacitor, and then you completely isolate it, so the charge Q on the plates can't go anywhere. Now, you slide a dielectric material into the space between the plates. What happens to the stored energy? Does it go up, go down, or stay the same? The answer is all about understanding how that dielectric changes the electric field itself, and therefore the energy stored within it.